Hello everyone. So it's 5:58. We will start in 3-4 minutes, around 6 to 6:03. We will start. Till then, we will wait for the people to join. So today we will discuss about the convolution neural network. In the last class, we also discussed a little bit about the convolution mathematics, the discrete as well as continuous function. So we will repeat that, and then we will discuss about a simple network called the LANet, and then AlexNet, and then VGG16. And yeah, it will go around 1.5 hours maximum. And then we will finish this lecture. Yeah. So yeah, we will wait around 1 or 2 minutes more. Yeah, let's start. Anyway, this video will be getting recorded, so anyone who wants to watch later, they can watch. So basically, the CNN, that stands for the convolution neural network. Convolutional neural network. The convolution is basically a mathematics concept. So that is defined as f of g of t as a integral of f of tau into g of t minus tau into d tau. So what does it look like? So basically you can see this function is dependent on time, and we are integrating over the d tau. So basically you have a function, let's say this is ft, and then there is another function, let's say gt, and then we are multiplying in and integrating it. So basically when we do the integration of two functions, we are trying to find out what is the overlapping area basically. So at t equal to t here, at this point, this is the basically the area, that is f of g of t. So basically let's try to plot it here. So if this function is moving with time, and if it comes here, then this is the overall area, convoluted area. The convolution means this g is moving with time on the right hand side. Okay. If this function is here, the area will be remaining same. If this function will come here, the area will overall reduce. And if it comes here, the area will reduce. And let's say the area will remain same here as well. So overall, the function looks something like this. And this is basically f of g of t. So this is the overall area that is changing with time when we are doing this integration over d tau. And this is the basically you can call it d tau in some sense. Okay. So I mean, d tau is a very infinitesimal quantity that is changing over time and we are integrating over it. So this is the overall area that we are getting. So this is basically the mathematical convolution, or this is the continuous function of the convolution. Right? If you have to write it in a discrete way, basically you can say that this function is denoted in a way that these are your points that you have plotted over the time. These are your like some kind of a scatter function. And this is your, let's make it yellowish. And this is your GT. Oh, let's, okay, just a minute. So when you are doing the discrete multiplication, basically you are doing this multiplication of this into this, this into this into this, and then you are adding it, right? So you can write this as a G1 into F1 plus G2 into F2 plus G3 into F3. And you can see that G1, G2, G3 is not changing. It is only moving in the time in the right hand side. However, this is Fn, this is Fn plus 2, and similarly this is some Fk, right? Because this is Tk, something like this, right? So this G is called the convolution kernel and F is the function. So this kernel is moving on to the function, and whatever is the weighted average of G over the F, that is the convolution. And if we are taking into the time, then this is the overall the discrete convolution function. So in this case, you can define G as a G1, G2, G3. However, F1 is defined as F is defined as F1, F2 up to Fn plus 1 up to Fk, let's say. And instead of 3, if this is a M overall the M values, you can call this as a GM up to the GM. So this is the kernel and this is the function. And we are multiplying the kernel with the function, and this kernel is moving over this function, and we are taking the area over that. And in the discrete, you can call it as a weighted average. Not weighted average, the weight basically. Or you can do the element wise multiplication, right? So basically, this is the element wise multiplication. So this is a 1D example, right? You can write this mathematically as G of tau into f of t minus tau, or tau goes to 0 to, let's say, infinity or some k value. Okay. Where one point
Here you are writing G tau into Ft minus tau. But
Yeah, there
when
is a
you did the multiplication, you did G1 F1, G2 F2, right? So I think so you did G tau F tau.
yeah. So let's okay. So I started with
Correct?
here, right? I started with here. Okay.
Yeah. Yes.
Let's take this element. Okay.
Mm-hmm. Mm-hmm.
And here I have a three element, and here I have three element. So basically, then I will be multiplying Fn into G1 plus Fn plus 1 into G2 plus Fn plus 3 into G3. So basically, here is a mistake, a small mistake. This is the T minus tau basically, because G is moving, and this will be always a three element, and this will be changing. Okay, because I have the k number of element here. Okay, so this will be always the same because the number of kernel element will be always the same, which is moving in the time. Okay,
Mm-hmm.
so I think your doubt is clear now, right?
Uh, yes.
I mean, you assumed that this will be always the case. So I have to take a more general case
And the
where,
case.
right?
Mm-hmm. Okay. Okay.
So great. Yeah. So this is basically a 1D convolution. If you are doing the 2D convolution, you can similarly create a 2D function that is f of uh, that is like let's say that is dependent on the space. Let's say if I'm that this is on the time. So let's say this is x comma y, uh, x minus h into y minus k. Let's call it something m into g into dot m, something like this, right? And then you integrate it over d h into dm, something like this, right? Over 0 to infinity, or whatever you can write this as a and b. If this is it between certain, like if something the area is limited, then you can call it a and b, or it is between, like it's just like you can write a and b here and c and d. So it is just the matter of kernel you want to roll in into your function, right? So this is the kernel, this is the function, kernel, and this is the function. So how does this will look like in real life? So let's say you have an image. Just a minute. Yeah. So let's say you have an image of m cross n of dimension such that each dimension is a pixel. Okay. And then you have a kernel of dimension a cross b. I mean, don't try to map this a and b and c and d to the previous example. They are just the number. Okay. And then what I am doing, I am placing this to this to this place here, and then I am multiplying this element of this matrix F of and the element of G, and then I am adding it, and then we are saying that we will get a value that will be the one convoluted value. Then we will move one row, one column on the right hand side, and then we will get the another value. So basically, we have moved one row at a time. Then we have the terminology that is called a stride, and we are calling this stride as a one. If we are moving, like let's say earlier we were doing this multiplication, and then I am doing this multiplication, means I am moving two rows at a time. then I will call the stride as 2. Okay, for this convolution neural network. So we are also going through some terminologies within this tutorial. Okay, so similarly, if you will keep moving like this, you will keep going until you will reach there, and you will say that okay, now I will move a little bit one row downward, and then I will keep doing this multiplication. Okay, so now let's say if I have this m cross n matrix as a function f, and if I have a kernel of dimension a and b, where m is much greater than a and n is much greater than b, and those are the integers. I mean, call it a natural number in this case, not integer. Then what will be the dimension of the convoluted value? So it will be basically m minus a divided by the stride s
Straight
plus 1.
plus 1.
Right, right. Similarly, the other dimension will be n minus b divided by stride plus 1. Right. In this case, our s is 1. So basically, let's say this m is 6 by 6 and this a is 3 by 3. Then what will the dimension of this? 4 by 4, right? Just take a small example. This is, in this case, this is 3 or 7. So let's 7, x dimension is 7, and this is 3. So basically, if you will move, then
7
this is the
minus
1.
3 by 1 plus 1.
Yes, so
5.
basically
So
it will,
5. 5 cross
right.
5.
Yeah, overall it will be 5, right? So
5 cross 5.
similar. So if you have the stride of 2, then this formula will become something like this, right?
Different. Yes.
Now there is another concept called padding. So why this padding is coming into this picture? So let's go a little bit back, little bit here. Uh, Here, let's say if your function starts from here, but you are starting your convolution from here. So if you have some element of g here, and then you have an element of f as well, and you want to take the elements, like if you don't want to miss the values of f, so you are creating some uh, you can say null values of f at these regions, and you are saying that f is 0 here, such that if you will multiplying the value of f with g here, I will only get some value at this point, and otherwise I will get the 0 value here. So basically I am adding some element in the right left hand side. Similarly, if the g f ends here, but I want to keep my g until here, then I will add some element of f here, so that I don't have to create any if else condition at these places. Then I will add some padding, that is, I will add those elements into the f at the left hand side and the right hand side, and I will call this as a padding. So let's say I have a f has a dimension of m cross n, and let's say I have a g of dimension 3 cross 3, and after convolution I want the dimension to be m cross n only.
M cross N. Same as
Having the
input.
and giving the information that my stride is 1, then how much number of padding I need to give on the left and at the right, and the left and the right, or the top or the bottom? Can you tell? The formula is m minus a
Minus
by
A.
s plus 1, right?
This should be equal
And
to 1. M.
so let's say stride is 1, and if the dimension becomes m minus 3 plus 1, that is becoming m minus 2,
So
but
A
I
is equal to
want to
1.
and I want the overall dimension to be remain m, then I have to add 2 as well, right? The
Yes.
stri the padding should be 2. The 2 means one at the left, one at the right, right? Right? In that case, I
Yes.
will make the I will make the formula. I will basically improve the formula such that this will become m minus a plus 2 into p divided by s plus 1, right? Because I want one padding, so I have to add the two values. If I want two paddings, then I will add the four values, right? So this is what the overall this convolution will look like. Okay. If I am not changing the dimension after the one convolution layer, one convoluted layer, not the convolution layer, convoluted layer. Overall, the convolution layer will look something different that we are coming there. So keep this formula. This will come handy when we will solving some problems. Okay. Okay. So how a simple convolution layer looks like. So let's say if we are taking an example of a handwritten image, let's say this is your image that has a dimension of 32 cross 32, where something A is written, not A, let's say 0 is written, something like this. So it has been divided into 32 pixels. Okay. And let's say this is a gray image. So it has a dimension of 1 into the Z direction. Okay. If it is a RGB image, then it will have a dimension of 3. Okay. Currently it is a gray image, so it is a dimension of 1 into the Z direction. This dimension. So this is 1 basically. So this is a 1 value. Now I am creating a convolution layer with the kernel of 3 cross 3. Then my dimension will become, with no padding, then my dimension will become 30 cross 30, right? With a stride of 1, right? Let's say, however, I want multiple kernel to be run on this image. Like let's say, when we do any kind of neural network training, these kernels is what we are basically training. These are the values what we are training. So let's say, take another example. Let's say you have an image of a home, something like this. There is a picture. These are the pixels. These are the pixels. And then what you are saying that you want to create a, another picture out of this, and you want to filter the edges. Let's say, let's be more particular. You want to filter the vertical and horizontal edges. So what will you will do? You will call this as f, and you will calculate the dou f by dou x and dou f by dou y, and whatever is the gradient, that gradient is giving you the edges. Basically, the edges where the overall the color changes. Like let's say this is a gray image, and wherever there is a edge and there is a white color, then there is a high gradient at this, right? So you will the this will pop up the uh, vertical vertical edges, and this will pop up the horizontal edges, right? So if I am introducing a kernel that looks like, let's say that looks something like this, like this is 1 0 1 2 1 0 minus 1 0 minus 2 1 0 minus 1. And if you are applying this uh, kernel onto this picture, basically you are calculating the central differencing over the this image into the x direction, right? And this is giving you
Is it X
the,
or Y direction? It is Y direction, right?
no, this is x, right?
Because yes, Okay.
Like let's say you have an element here, you have an element here, and you are not giving any importance to the middle value. You are taking this value, you are subtracting this value, then you are trying to find the difference into the x direction, right?
Yes, but in del f by del x, you have written vertical. It should be
No, no,
horizontal, right?
no.
Okay.
Del f by del x, I am doing this into the x direction, and this will pop up the vertical edges, right? Because
Mhm.
if if there is a large difference here, then this will pop up the vertical edges. Let's say if you have a edge here and there is no change in this value, and whatever the value you have here and whatever the value you have here, if you will
That is
try to
same.
multi, so it will now pop up the horizontal edge, right?
Okay. Got it. Thank you.
Yeah. So this will pop up the vertical edges. So these are the trained filters. We know that this filter will always pop up the vertical edge. If I have something like this, that is 1 minus 2. I mean, why I am giving 2 in middle, I just saying that the middle value I want to give more importance. Okay. There is no other. I mean, you can call this 1 as well. Okay, I have no issue with that. 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. So this will give you the value of dou f by dou y, and this will pop up the horizontal edges, right? So these are the filters that we know that this will always create the vertical and the horizontal edges. But when you have the image, complex image, you don't know what kind of filter will create what kind of uh, edge detection or what kind of overall feature detection. So basically, in that case, these features, these kernels will be acting as a training parameters. So you initialize a 3 by 3 kernel, you added some random values of uh, W's within W1, W2, W3 in this 3 by 3 values. And once you will be training those, these W's will be get trained, and then it will learn to create the features out of your original image. Okay. So these we don't know originally what it looks like and what it will do. But let's say I am solving a classification problem. Then while the training, it will get trained and it will try to create some features out of this image. Okay. Yeah. So I just wanted to clarify, because if I am moving ahead and if you don't know that we already know this or we don't know this, then there's no point of knowing why we are doing convolution. Okay. So let's say I did one convolution. I got some features. I got a feature here. And then I have created another 3 by 3 kernel, and I did the same convolution on the original image, and I have created another 30 cross 30 feature. Now we know that this has been randomly initialized, this has been randomly initialized. So those two will create two different kind of features, right? Similarly, let's say I have created 10 such kernels, then my output image, like let's say my input was of dimension 32 cross 32, then I added a convolution with 10 kernels of dimension 3 by 3, then my output dimension will be 30 cross 30 cross 10. Understand? Understandable? No problem, everyone?
Uh, does it mean that we are dividing into this many classes, or
No, forget about the class right now. Let's call
Mhm.
20 kernel. Okay. I have 20 kernels.
That means 20 time 20 layer neural network, correct?
Yes, like let's say you have an image, something like this. Uh,
Mhm.
Sorry. Of dimension 32 cross 32.
Yeah.
and then you having
Convolving
these
by 3 by 3.
these
Okay.
numbers of kernels. Okay.
Okay.
And then you are creating these number of, these are like, in this case, these are 20. And this is 32, 30 cross 30. This is.
Okay.
Okay. And remember, these are the trainable. So each kernel is different. And each kernel will learn something different. Okay. Because in this
Sir, will it be
picture,
in the same pass?
what? Can
It
you
cannot
repeat
be in
again?
the same. It cannot be in the same pass, no? One after another we have to do, right? Or how?
No, you can do in the one pass only. Like, let's say if you have this, image, okay. So one of the kernel, let's try to find out the vertical edges. Okay.
Okay.
Another kernel will try to find some curved features. Some kernel will try to find some horizontal edges. Okay. If you are trying to create one kernel from the original image, and that has a dimension of 3 by 3, then you don't expect this image to be creating these different kind of features in through these kernels. Understood what I mean?
Right.
Like, let's say if you are training these kernels of 3 by 3 dimension, and you have one kernel and you are directly passing from input to output, then this will not learn everything of this image, right? Because it is only of nine. It has only 9 inputs inside it. So either it
Correct.
will
Yes.
learn
Yes, sir.
something like this,
Yes.
or it will learn something like this, or something like this, right? By
Right.
changing their values.
Right. What I said is 30 by 30 image that we'll get intermediate result. Each of that 30 by 30 intermediate thing will give only information about one feature from one kernel, right?
Yes.
Okay. Okay.
Yes.
Okay. Okay.
Let I
No,
understood your
no, I
earlier
don't think
question.
so. Here, see, what I understood is 3 by 3, 20 kernels. What we he has taken is there are various different filters or weightages. For example, they are doing different things, like they are finding horizontal or vertical, or they are finding some sharp edges or anything. Now, when we are convolving the first one with the 32 cross 32, then whatever he has drawn, the multi in between, right, 30 into 30, the first layer will be coming, right? When you
Yes.
are convolving the second kernel, then the behind one will be coming. And this is the same interpretation of the same image in a different way, what the kernel wants to do. And
Exactly.
overall, correct? So
Correct.
overall, it
Each
will
of these
make us some
30,
difference. Yes, exactly.
right. Each of these intermediate 10 or 20 intermediate
Hmm.
or images is there. It is going to give me only information about one feature corresponding to that kernel filter.
Yes.
Okay. Right.
Yes.
So earlier you like told like bypassing this to create another filter, right? You can create, like, obviously there are different layers, but let's say you have created only one out of this, and then you are going to the second layer. Basically, you have already lost a lot of information about this, right? Because one kernel will not be able to take all the information from this original image, right? So that's why you need those n numbers of kernels.
Okay.
Now, okay, so this is not overall one convolution layer. So let's add few things. Now, I have created this some interpretation of this original image. Then I will add one activation layer. Let's call it activation layer here. So I will pass through some activation. Let's say ReLU or 10H. I will talk about like why ReLU or why 10H or why not 10H later. And then whatever the output I will get here, that will have a same dimension of 30 cross 30 cross 20. and then I will do a pooling. So pooling is like, let's say I have an input of 10.
16 8 গলে 8 0 1080.
Yeah. So let's say I have an input of 4 by 4, and each has some element. Those are different. And I am saying that I will take a stride of 2, and I will say that I am trying to find the maximum of that value. So what I am doing basically here in the pooling, I am taking this 2 element and I will find the maximum of that, and I will write here. Again, I will take the maximum of this, I will write here. Again, I will take the maximum of this and I will write here, and I will write there. So basically the dimension has been reduced directly by half. Either you can take the maximum value, either you can take the average value, or I get. So these are the kind of pooling uh, calculations that are available into the literatures. Okay. So after doing this activation, I will do the pooling, let's say. And in this case, I will have a dimension of, after pooling, activation plus pooling, let's say I'm saying, then I will have a dimension of 15 cross 15 cross 20. Okay.
With stride 2 or 1?
In this case, stride 2. Suddenly the dimension has become half. Okay. And this is one convolution layer that contains one convoluted plus one activation plus one pooling. Yes, Nivedita. Question?
Yes, sir. Good evening, sir. Sir, how many strides we can take?
Generally, in the literature, in the pooling, I have seen generally people take 2 by 2 mainly. However, you can take like different. We will come to few examples, and then we will see that somewhere people have taken 4 by 4 as well. But it depends what kind of problem you are solving. Okay. So it's no hard and fast rule. So we will come there. Okay.
Okay.
Yes. So this one convolution plus one activation and then pooling, this sequence is called one convolution layer. Okay. And after this, you can do the same thing. Let's say this 15 by 15 cross 20 has been converted into, let's say after 3 cross 3 into, let's say 40 kernels. This will become 12 cross, 13 cross 13 into 40. And then let's say if you are saying that after doing the padding of 3 cross 3 stride of padding of 1 and 3 cross 3 stride of max value of pooling, it will become basically something like 5 cross 5 cross 40, right? It will become 15. And then if you will take 3 3 3, then it will become 5 5 5, right? Understandable?
One question, 15 13 I understood, but how 20 and 40 became 40?
Yes. Okay. So how 20 became 40, that is also a different question. Like let's say you have a 20 sequence. This is your 20 sequence.
Depth. Yeah.
Okay. This. And you are converting this into a 40, let's say. This is 20, this is 40. So what you are saying, so when I will take this convolution of 3 cross 3 or something else, With convolution, I will do some other computation as well. Like let's say I have this first layer, I have the second layer, I have this third layer, I will have fourth layer. So along with this 3 by 3 uh, convolution, I will take averaging of, let's say this is the first element, second element, third element, fourth element, fifth element, sixth element. So I will take, like say, let's say I will take the 3 by 3 of zeros element and the first element, and then I will average it and I will call it as its first element. Okay. If I am taking the average of first and second after convolution and I am calling it as a second element. I am taking the average of second and third and I am calling it as a third element. Okay. So if I will do that, then I will get the 19 element, right? Overall, in this case. Correct?
Okay.
Then I will say that, let's say if I will do the averaging of 0, first and second, and then I will say that is the 19th element. Then I will call one first, second, third, and then I will do that, call it as a 20th element. Then I will call it 3, 4th, 5th, and then I will call it as a 21st element. So this kind of averaging is, we are creating axis symmetry. I mean, we are breaking the symmetricity by doing this kind of averaging. Understood what I mean? So we have this kernel. We have the one kernel. I am passing this one kernel to the first, second, and third. I got these values of dimension. Let's say this is 15 cross 15. I got the dimension of 13 cross 13, and then I took the average of first, third, and I called it as a first layer or on any layer. Understood? So basically,
Yes.
so what it is doing, let's say the first layer was trying to create something like this. Let's say second layer was trying to create something like this. Okay. Mm, let's make it more representable. Okay, let's create something like this. So first is doing something like this, second is doing something like this, third is doing something like this. Okay. And if you will take the average, then this might look something like this. Correct?
Yes.
Okay. A very good question. That comes to another conclusion, that this was, let's say, layer 1 and this was the layer 2. Then as we are moving deeper into the layer, we are basically trying to create the features more, you can say,
Smoother.
more visible, more smoother and more visible to us. So you can say that the first layer we're trying to create the edge. The second layer is trying to create a better feature than edge, like combination of edges that is creating something like this or something like this or something like this, you know.
Yes.
Or, and if you will go deeper and do the same thing, you might be, let's say in this case, you might be able to create something like this, something like this, something like this, something like this, right? And since we are going deeper into that, basically we are saying that we are basically trying to compress my image and still getting the features that was there at input.
Okay.
Right?
Yes.
And we have also made this image size smaller. However, the kernel has been increased. Okay. Let's say after let's say after 3 convolution layer, I have a dimension of 5 cross 5 cross, let's say 80. Let's assume. Okay. After 3 convolution layer, and we say that, okay, this is enough for us. Now we are going for the classification. We have done enough with the image. Now we want to classify. So we will pass this to a hidden layer. That is the hidden layer, that is the multi-layer perceptron. That is MLP. that has the element, let's say 80. Okay. Now you can say I have 80 neurons here and I have 80 element here, and I am saying that each 5 by 5 will be passed to one of them, right? And since it has 25 element, each neuron will have 25 inputs as well, right? Then it
Yes.
can do the element wise multiplication and addition to create one output. Correct? So there is a convolution of 5 props 5 is happening here, right? To create one output.
Yes.
Understandable? Yeah. And then we will say like, okay, let's create one more hidden layer. This is not enough. So we will say, okay, let's create another 80 by 80. And this is what the typical MLP will look like, right? And then we will say that, okay, we are doing the classification. So we will say we have the 10 output here. Okay. And here, since we are doing the MLP, we might use 10H. We might use, here we will use 10H. But here we will say that since we are doing the classification, we will go for the softmax. And this softmax will create the score function, right? That means it will create the output between 0 and 1 such that the sum of all the output will become 1, right? And that is also the probabilistic output. Understandable? Any
Yes.
question? Yeah, great. So this softmax will create the output, and that will be the probabilistic output that will be also called as a score. Great. And that, and let's say if my input is after training, and if say that my input is 0, and if the score is maximum for the first output, I will say that I have predicted the correctly.
Correct.
Means the my neural network is trained in a better way. Means my testing is correct. Okay. And basically this is what a lay net neural look like. Neural convolution lay net CNN look like. So we will go a little bit like more uh, like correct numbers, but this is what a simple lay-net neural network look like. However, instead of 20, there are 16 neurons, and there are another 20 or something like that. That is a like how you want to create things. Okay, but I think you have understood the nuances of increasing these kernel sizes, right? And how it is helping it. Okay, okay. So this is what a simple CNN looks like, and then we will see some examples. Let me check anything else I need to tell before I go to a different PDF. Okay, so every one of you, I hope all of you have not watched all the lectures of week 8, right? So I just want to show you the exact same PPT that professor has taught. So that would be a better way of representing and telling how things work. Okay, so just give me a minute. I will stop sharing. Okay. You're able to see my screen, right?
Yes, we are.
Yeah. Yeah. So this is what we have already understood. This why padding we need. This is what the original image and the kernel looks like when we add the padding, what happens. Then we have already understood this architecture. We have also understood what the vertical and the horizontal kernel looks like. We have also understood, like, let's say if we want to create the multiple kernels, so how the dimension will increase, right? That we have also seen.
This is RGB, right? Three layer.
Here, this image, right?
Yeah.
No, this is just a representation that this is another one kernel, this is another kernel, and each kernel is creating a different output. Such that it has a dimension of, let's say, 32 cross 32 cross 1, then the dimension is increasing from 32 cross 32 cross 1 to 10. Or let's say it has a dimension of 3, then we are averaging it over the 3 cross 3, and then we are creating 10 different features out of the RGB. Okay?
Okay.
Yeah. Yeah, we will come to this later. We have also understood what the pooling look like. Pooling, okay, so just one few more words for the pooling is that we want to, we are trying to pop up the most important feature, and we are saying that the other things are not important for us. Okay. Like, let's say you have some picture of handwritten letter, and whoever has taken the image, there might be some shadow in the image, and there might be some darkness or some more glow in the image. So that will create the numbers into the pixel. And if you will take the pooling, then everything will be fade away directly, because you know they are not important. Okay. This is what we have discussed now. So you can see the summation of output will become 1. And if my input is both, then this softmax will create the maximum value for both if it has been trained nicely. Okay.
So,
Okay.
if you scroll up a bit, please. Yeah. The boat example. Here,
Yes.
the last fully connected, is it the one which you are saying that you are giving it to, say, those 40 layers, right?
Yeah, let's say some layer, some number of layer. Then let's say I have a 4 things to classify, and I have a 4 output, in which the 4 output are dog, cat, boat, and bird. So let's say if I am giving the image of, you can say the boat, and if my prediction is coming, like the probability is coming highest for the boat, then I'm saying that my prediction is correct, right?
Yeah.
So
But
this is,
just before that layer, that is
yeah.
MLP. Is it MLP?
Yes, it is MLP. Until
Okay.
this is we have the convolution layer.
Okay.
And
Is it the last two are middle, second last and third last are MLP?
Yes. These two are the these two are the MLP.
MLPs.
Yes. Yeah. At least 2 multi-layer perceptron we need. At least 2. 1 is not enough. Okay.
So for training these two also back propagation may be required, for example?
Yes, because these also has weights, right?
Yes.
Yeah, if we, let's say these are the images, right? Some kind of a, like, this also has some features, and then we are doing some element wise multiplication with their weights to create the overall output here. And then we are saying that, okay, if I will give directly this overall output of the softmax, this will not be able to do what we want. So let's create more depth. Okay. And this depth is enough, let's say. Then we will say, however, if you will see the networks later, the neural networks has around 16 layer of depth there. But out of 16, there might be like 10 convolution layers and 6 MLP, something like that.
MLP.
Yeah, so something like that. Okay. Yeah. So this is what we have known. So these are the simple understanding. Let's say instead of doing the CNN, you are giving the input directly to the MLP. So what will happen? Instead of having a dimension of something, let's say 80, And if your input of dimension 32 cross 32, and if you will flat, it will become 1024, right? And if you are giving a 1024 dimension as an input to your MLP, and then you are saying like, okay, let's create 5 hidden layer of, let's say, 100 or 1000 or 2000 in each layer, and then creating four output of softmax, maybe your training loss will become lower. But once you will start testing it, uh, it's a total nightmare, because neural network is not able to generalize. They are basically only training for the input you are giving it. Okay. So what is happening in that case, CNN is basically trying to create the features that is only important for you. Okay.
So
So
this
this
is
is
overfitting. With this, we are doing overfitting, correct?
yes. If you are not using CNN, well, yeah, this is overfitting because the test error is too high and the training error is too less. And in that case, your
Yes.
test loss will be so high, like maybe 80%, 70% you will be getting the test loss. I mean, 80% error is there out of, like, let's say you have 100 test values and you are getting 20 correct and 80 incorrect, then there is no point in that, right? So that's why you need the CNN. Yes. So let's zoom it a little bit. And this is what a simple LearNet looks like. So in this case, this has been used historically into the bank's ATMs to read the checkbooks, because earlier people used to write the checks, write the numbers, and make it automatic. And this LearNet was made by the most famous person, the LeCun, Jan LeCun. You know him, right? So I will give a little bit introduction. Like, he is the most courageous, the most revolutionary person into the ML, who does not follow the trends. He believes what he thinks, what his instinct tells. So yeah, try to read a little bit about him. He's a good guy. I mean, I like him. Yeah. So you can see that the 132 by 32 input has been converted into 6 using 6 kernels. Then 6 kernel has been pulled through after some, you can say, activation. The pooling is also called subsampling many times. And then after it has been passed through another layers, another kernels with different combination, that is increasing the dimension to 16. And then we are doing the subsampling again. And then we are giving this to the two hidden layers that has a dimension of 120 and 84. And then we are saying that overall the output is 10. So just the number we are changing. So you can see how this dimension has been increased from 6 to 16 here. You can see here, like, you have a 6 input here, that is 0, 1, 2, 3, 4, 5. And then you are creating the first output here. That first output is basically the convolution plus addition. So addition of convolution of first output, second output, and third output, and then addition. And that is giving me the first output here. Similarly, I am doing this cyclic thing until I have got this 6 output. Then I did the cyclic for this 4 output, and I have got this until 11. And then I did at some other combinations until I got this total 16 output. And you can see the last output is taking the averaging of all these outputs, right? So you can imagine, so these are creating the simple edges. These are creating the overall better features of the inputs. And you can see this. Uh, yeah, so I hope this is understandable to you, right?
Yes.
Yeah, so yeah, let's go there. Okay, so we will come to that image later. So this is what a simple LearNet looks like. And this was the winner of this uh, 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 I
Challenge.
mean, yeah, this challenge in 2012, I guess, right? Yeah, and then
Can you please explain that image again? That XX which you have mentioned, right? Scroll up, please.
this one,
No,
this,
below there was, yeah, this one. Yeah. How this is
yeah,
interpreted.
yeah. I told you, like, I have a six output, 0, 1, 2, 3, 4, 5, 6 here, right? And
Okay.
out of six, I am creating the 16, 0 to 15. Okay. So the first
Okay.
output is being created using the first, second, and third. That is, let's say it's a dimension of 30 cross 30, or let's say it's a dimension of 14 cross 14. And if I am doing the convolution with the 5 cross 5, so my dimension will become here 10 cross 10. Okay. It will have a dimension of 10 cross 10. It will have a dimension of 10 cross 10, and then I will take the average of threes, or I will add three of them. And that is my first output, this one.
Okay.
Got it?
Mhm.
Similarly, I will take the second, third, and fourth. I will do the convolution for second. I will do the convolution for third. I will do the convolution for fourth. And then I will take the average of those, and I will call this as a second output of this convolution layer.
Okay.
Got it? And
Mhm.
similarly, I will keep doing, and I mean, like, let's say this is a cyclic method, right? Like I got for 0, 1, 2, 2, 1, 2, 3, 2, 3, 4, 3, 4, 5, 4, 5, 0, and like 5, 0, 1. So this is a cyclic, right? I took the three values, I mean,
Mm.
three inputs, and I made the six output, right?
Yes.
Then I took the four values and I
Four
created the another.
continuous. Four continuous
Yeah,
values.
yes. I came up to here. I'm
Mm.
not sure here, up to 11th, 12th part, right here.
Till tenth.
And then, no, here, like
Tenth.
G,
Till tenth, it is
no,
continuous.
no, this is also continuous, like 5, 0,
Okay,
1,
yeah,
2,
yeah,
3,
continuous. Continuous.
right?
Yes, you're right. Mm.
Yeah. And then I took like, okay, let's create
One space.
one space, then two space, and then whatever I have left, I will take the average of all of them. Okay. So
Mm.
this is what you will have to design it. Okay. While doing the CNN, how much output you want, you will have to design this. This will not come directly to you in any, like let's say you are creating your own CNN, you are not using any pre-trained network, then you have to design how you want to create the feature from your previous layers. Okay. However, like these are the very classical old models. So when you go to study these CNNs, when you start your machine learning journey, you directly import these networks, you train over some data, and you test it, and then you do some hyperparameter study, right? So these are the initial kind of process you go through. But let's say you have your own image and you want to do some kind of classification, then you have to understand your data. So how the data is acting, what kind of features are there in the data, what kind of kernel you need, how much number of convolution layer you need. So these are not not is something that is you cannot understand. Like these things are, like let's say there is no scientific rule to do it, but there is a good understanding behind it who has made it. Okay, like so you have to understand your data before you create any such fundamental model by yourself for your input. Okay, I'm just trying
Understood.
to tell you that.
Understand. Thank you. Yeah.
So don't assume that these are the rules that you can do everywhere. Okay, yeah, I'm just
Agree.
okay. Yeah, so basically these things are breaking the symmetry and they're creating better features out of these edges. Okay, then we have this. Yeah, now there was another model that is called LXNet. So LXNet was created with the data set of around 1.5 million. And out of 1.5 million, there were almost the image that were classified into overall 1,000 type of different kind of output. And each kind of output has around, like let's say if I have like I have 1,000 images of flower, 1,000 images of horses, 1,000 images of cars, 1,000 images of boats, something like that, such that I had total almost 1.5 million of images, and 1.5 million images were fed to this LXNet, and we were classifying into the 1,000 different kind of output. Okay. So earlier we were classifying only 10 output.
10.
Now we are, yes. Now we are classifying the 1,000 outputs. Okay. Now the problem is very serious. Images are more messy. So let's see how the image looks like. You can say that this is a dog. Like earlier, when I was had the image of 0, 1, 2, 3, there was nothing in the background. Either the 0 was shifted little bit in the left, or it was into the little bit right, somewhere in the center, somewhere in the top or bottom, but it was not something behind that, right? So there is a more chance of error in this kind of data. So how this network look like? You can see that each image has a dimension of 227 into 227 cross 3. Means each input is a RGB image.
RGB.
Yes. And then we are doing this convolution. So let's take overall look, then we will go one by one. So you can see this is a one convolution layer. Then we have the second convolution layer. Then we have some simple convolution layers, without max pooling. Then one max pooling is there, and then we have some hidden layers. Okay. And then we have the soft max. Okay. So these are the simple way of representation. So we will go through the simple mathematics. So you can see that my kernel size is 11 cross 3. And then we are doing this convolution and we are averaging over this RGB. Okay. So that's why we are not saying cross 3 here. But when you will be defining into the code, you will have to tell that this convolution will create one output for one kernel. If I have a 96 kernel, I will create 96. Otherwise, you will have a fourth dimension as well, and that will look like 55 cross 96 cross 3, right? Because this is also a dimension. So basically, we are averaging over the Z value. That is the RGB value. And the RGB value does not tell a lot. Like you can see in these examples, we are not caring about the colors because we are more worrying about the features, that is the edges or we are not creating a new images, so we don't care about the image, the colors. Yeah, forget about this diffusion models for right now. So we are only care about the classification. So we only care about the features, and features means edges or the curvature and everything. So in this case, I am creating a 11 cross 11 and such that, and my stride is 4 with no padding. In that case, I will get an output of 50 cross 55 cross 55, and I am creating 96 such kernel. So I will get the dimension of 55 cross 55 cross 96. So basically, you can calculate it. So it will become 238.
216 divided by 454 plus 1.
Sorry. Yeah. So sorry. 216. So it will become
54.
54 plus 1. Right. So 55.
Yeah.
Okay. So simple. Then yeah, we are doing max pooling of a stride 2 of 3 by 3. Yeah. So someone was asking, do we do the max pooling of 3 by 3 only? No. Well, 2 by 2 only. You can see we are taking the max pooling of 3 by 3, and we have the stride of 2, right? So you can see that.
So from every 3 cross 3, we'll take the maximum value and then we'll take stride 2, correct?
Yes, like let's say I have taken I have a 3 by 3 kernel. I mean, not a kernel. I have a 3 by 3 window. I have gone to the topmost value. I got the maximum value. And then I have shifted it by 2 rows or 2 columns. 2 columns, right? And I
Yeah.
again took the maximum value, and then I get shifted by 2 columns. And once I have
Yes.
finished with my one, you can say from one channel from left to right, then I have shifted 2 in the bottom, right? So that's
Two row in the bottom. Yeah. Yeah.
yes, 2 rows into the bottom. So this is what it will look like, right? So
Yeah.
basically it depends on you how you want to do it. There is no such rule. Okay. And this is what your output will look like. Then again you did some convolution. And from 96 you have created the 256. And let's say you are doing a similar kind of a strategy like you did earlier, but you will have to design that strategy. This will not come to you directly, right? And you have designed some strategy to create 256 output out of 96. Then again you did some pooling. You have got the output of 13 plus 13. And then you did some convolution without pooling because 13 cross 13 is a good enough small image. We need to find more features. So we are basically deepening the layer without removing the features. Basically, you can say removing the noise. Like pooling generally removes the noise, right? And we are saying
Yes.
that 13 cross 13 is good enough. It does not have noise. Now we are building the features. So we are not doing any more pooling. And now we have built the features and we are saying that maybe there might be some noise. So we are doing another pooling. And then we have got overall output of dimension 6 cross 6 cross 256. Then I have fed it to input
MLP.
of MLP of 4096. And in this case, they are saying that they are not doing the convolution here. They are saying that they are flattening it and they are getting the overall element of 9216. And this is directly get fed into this forward forward layer. Okay. Earlier we
That
were doing
means
so. Earlier,
each pixel is fed as
yes,
a
each
bit,
pixel.
right?
Yes,
Each
yes,
pixel
each pixel is as an input. Correct.
input.
Here we were using as a like this was my overall output. So this output was we were giving to the one neuron. Okay. However,
Yes.
we are not doing this here. And we will know later that this will create some error. Like I think this was the runner up, I guess, some time ago. I think. Okay. So you can see that these numbers are way too large. Okay. Like I'm not sure. We will go a little bit here and we will see that. Okay. So it has 60 million parameters. And when this was discovered, we had around, I'm not sure, we had A40 GPUs at that time. And I am not sure A40 or L40, like if NVIDIA GPUs, right? And those were not good enough to train such network. So we created a strategy such that we did little bit of uh, like input divide, like we divided the input such that the overall the features has been divided into two such layers, and these layers were sharing the output after each convolution layer, and this was created using two networks. So like you can see this, like the lower one is fed to one network, the upper one, I mean one GPU, the upper one is fed to another GPU, such that we are dividing the number of parameters for the each GPU so that this can be trained. And this network, when it was being trained, they used to take a week to train for this kind of data. Okay. And this network was used to show the error of 15.3% for top 5 error rate. So what top 5 error rate mean is that, let's say, I have given the input of a flower and I have got some output, some thousand output. And if I am saying that in top 5 output, if I am not getting the flower, then that is the error. Okay. Like let's say, like I have got 5 top outputs, and in top 5 output, if there is not flower, then I am calling it as an error. Like we are giving some flexibility to say that what is error now. Okay. We are not saying that if the top one is flower, then it is correct, otherwise it's not error. Otherwise it's error. We are giving the flexibility here because we are saying that, okay, the outputs are too large, the classification is too big, the image are too lengthy. I mean, inputs are too lengthy. So even in that case, the error was around 15%. However, in the LANet, the error was around 5%. So basically, if you will compare how the error was calculated in the LANet, this might become around 50% or even 60% in that case. Okay. So, and all these networks were calculated using the backpropagation. Okay. Why I am saying backpropagation? Because when the neural networks came into the picture, there were some other way of training the networks as well. Okay, like there were some sorting methods. Like let's say you have a one weight, you change the weight, and if you see that your loss has become smaller or not. And if the loss has become smaller, you will go in the similar direction for that weight until you will say that, okay, my loss is not getting smaller, and you will change the another weights. Okay. Now that is not a back propagation, right? That is shooting. Like randomly you are doing it. And you don't know until until when you will keep doing that. So that is a more expensive method. So all these training were done using the back propagation of proper certified mathematical way. Okay. 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 Yeah. Now we will see some problems in this training. So what happened? Let's say you are training this AlexNet. You have given some input, and that input have a lot of sharp features in the RGB. And in that case, your output is too large, and then you did some max pooling, and you did one convolution layer. You got some output, and the outputs are too large. Like your numbers are too large. However, you are passing through, let's say, a ReLU, and what happens when you do the backpropagation, you calculate the gradient, right? And when you calculate the gradient for the ReLU, when the values are greater than 0, you will get a very large gradient value, right? It's around 1 or uh, whatever the slope is. And in that case, there is a good chance of, let's say, if the slope is very smaller, then you will get the vanishing gradient. And if the slope is very large, then you will get an exploding gradient. So the idea was to keep the values smaller so that the value could always calculate this value with the smaller slopes and not small enough that it goes under the vanishing gradient. That's why we did some local normalization. And the local normalization looks like let's say if you have these values, and you are doing some kind of, let's say, uh, what you can say, kernels, and these kernels will try to will try to take the value of like it will try to take the element wise multiplication and addition, and then it will divide by the square of all the element of their original values, and that's how it will become the overall normalized value. Okay, and this is what it is doing. This is taking the square of that value, and this is basically the overall convoluted value. And
But what is beta here? I didn't understand that.
beta, I mean, let's say uh, beta can be any hyperparameter. You can say, like, let's say you are getting, after doing this, after doing all this calculation, assume there is no beta, and let's say you got the value 0.9, and you said like, okay, I want the value between 0.5 and something. So you use the beta of 0.456, and the value normalized to, let's say, 0.5, 0.45, something like that. Then beta is just a hyperparameter. Understood that, right? K is another hyperparameter, alpha is another hyperparameter that you have to tune when you are doing the normalization. K is another value, like let's say you did all these square addition and you got the very small value.
Zero.
Such,
Zero.
I mean, you will not get the zero values because you are squaring it, but you will get nearly zero. In that case, you will have to add some value. Otherwise, it will show to infinity, right? I mean, 1,000, 2,000. And this is what we are not trying to create. We are trying to create a smaller value, right?
Right.
Or maybe you can say that A is a large number, but B is a smaller number. In that case, this will become the ratio will become very large. Then I have to keep the beta smaller to make it as a large value such that the ratio will become a smaller. So beta is a kind of hyperparameter. Okay, so
Thanks.
you got it right.
Yeah.
Then there is another thing that is called dropout. So what dropout means? Since your images are so dense, so complex, and you are training for such large input, you are very prone to uh, overtrain it. Overtrain means your test error is going to be large, right? In that case, you want to say that whatever your network is, it needs to generalize things. Okay, like let's say I have a one multi-layer perceptron here, and this learns to tell that if I have a flower as an input, this is always going to give me output of uh, flower, output maximum for softmax for the flower. However, if I will give something input different, this is not going to contribute to me at all. However, this is not we want. I want that this weight to contribute for everyone else as well. Otherwise, what will happen? Uh, some, uh, I mean, if this will not contribute, because we are trying to generalize for all the other inputs, I will get a very large error for something that is similar to flower that is not flower. Like let's say I have a color of car that has the same color as a flower, then it might show that this is a flower, but that is a car, right? So we need some dropout. So dropout what does? Like let's say I have a 4096 neurons here, and I am saying that in every epoch, I will deactivate the 50% of the neurons, and then I will do the back propagation. So out of 50%, once I will deactivate that, neither they will participate in creating the output, neither they will participate in creating the back propagation. And then I will change the weights. Again, in the next epoch, I will switch the another next 50% or another 50 random 50%. And this dropout will help in generalizing my network. Otherwise, such large networks generally doesn't train very good for the very complex data set. So you have to pick up the different training strategy, and these are called the training strategy, right?
Yes.
And yeah, so what is that? 7. Yeah, so this is what I was talking about earlier. You can see the first layer is just generally trying to create edges. The second layer is trying to create more deep features. The third layer is trying to create much better features, then more denser feature and more denser feature, right? So this is what they are doing. And if they, you will not create those kind of, you can say, the averaging of the previous features, you will never get this, right? And we understood how we are getting that, right? So this is the overall idea is. And similarly, we have the other network that is called Visual Geometry Group by the Oxford that is also doing the same thing. However, like previously we were using the convolution of 11 by 11 or 5 by 5. Here they are using the convolution for 3 by 3 only. Okay. And since they are using the convolution of 3 by 3, that's how basically, mm, like
I think so
let's
with
say
padding, right?
in this case, this is the padding because the dimension is not changing, right?
Same. Yeah, it is same. Yeah.
Yeah. And let's say they did the max pooling, the dimension has been changed. They are adding the padding, but they are also saying that while doing the convolution with 3 by 3 with padding, I mean, with padding, I'm always doing the kernel size of 3 by 3. So let's say I am doing the kernel size of 3 by 3. I have a over total number of parameter that is to be learned is 9 only. If I have a kernel of 5 by 5 or 11 by 11, the number of parameter that to be learned is around 121 or 25 for a single layer, right?
Mhm.
So if I have an input of let's say some n by n, and I am trying to get some m by m at the output, instead of creating directly 11 by 11, I will create a number of 3 by 3, and then it will get converted into m by m. Understood what I mean, right? Like, well, let's say I have a dimension of 56 by 56. I am getting the output of 56 by 56. But in between, earlier I was doing a kernel of 11 by 11 with the padding. Right now, I will not do that. I will create a 3 by 3. Then again, I will get the output. I will again create a 3 by 3. Again, I will get the output. Again, I will do 3 by 3 with the padding. And whatever the output I get, then I will give it for the pooling. Okay. So you can see that these number of convolution layer with the uh, uh, same size of kernel, and the same kernel we are using, then we are reducing the number of parameters, right?
Here, what is the meaning of nected?
Yeah.
Nected, blue one, which is below mentioned, right? Fully nected.
Fully connected. Okay. This is
Connected. Oh, connected. Okay.
yeah. Okay.
Okay.
Understood.
Connected.
Right.
Understood.
So this is the simple like previous one, but less number of parameters, more simpler network, more well understood network compared to the previous one, like little yet less messier, right? So, and this is what the overall VCG looks like, and this creates uh, a 7% error compared to the previous one. Okay, so yeah, and then transfer learning, and then what it is, let's see. Okay, so we already know the exploding gradient and the vanishing gradient, right? So what does the transfer learning does? So you can see that in this case, the convolution layers that has been trained, they have been trained to create the features from the input. So what they have learned? They have learned to create the edges. Then they have learned to create the features from the edges. Then they have learned to create features from the features, right? And then if you are giving any new input that is not into the training set, they can still do this kind of thing because they have trained kernels inside them that can create those kind of features, right? So you can directly use those kind of convoluted convolution layers into a new kind of data and a new kind of training. And this is what exactly the transfer learning is called, right? Any problem?
I understood it is like this, that for example, you have already trained your model, correct? So
Okay.
initial layers, right? After the first input, whatever outputs are coming like edges, etc. of your model, I can take it as an input for my model. I don't need to train that into that level. Is it like that?
Yes, yes, but
Like that
only,
only, right?
yeah. Like you can save the weight matrix, and you are
Yes.
saying that okay, if my input size is same as the previous one, I can directly give that as an input to create the output for the convolution layer, and then I can create a different MLP, and then I can do the different kind of classification. So my
Right.
training will be easier. Like I'm not saying that once you are doing the transfer of weights, you are not training those. You definitely you will be fine tuning things, but you can directly make your training easier. Okay.
Correct.
And this is what the overall this week is. Yeah. So let's go to some problems. Let's stop sharing this one. Okay. So the previous year. Yeah. Let me share. Yes. Okay. So yeah, let's solve these questions and then we will finish this week. So which of the following is false about the CNN? The question is which one is the following is false? Yeah. So I am expecting the answers. So yeah, output should be flattened before feeding the FNA. Yeah, it is correct.
False.
Flattened means
B.
within range of 0 to 1, correct?
No, flattened like let's say you have output of 5 cross 5 into 80 or something. Then you are converting that into a smaller chunks, that is the bit by bit. That is called flattening.
Lower dimensions. Okay.
Yeah, for providing it into the MLP. So that is called flattening. So you are definitely doing that. That is not incorrect. That is the correct, right?
And C is what is that? We can use many
As ma-
as
no,
many
so
as many. I
as
think so. As many.
yeah. So
Yeah.
the
I think B.
B can be false.
there can be only one
We,
fully connected. Yeah,
we
like
can have n number of fully connected layers, like what
yes,
you
yes,
said, MLPs, correct? Yeah.
yes, correct. So this is the like there is no fixed rule, right? So obviously this is the incorrect, right? Option B. Yeah. So question 2 is input image has been converted into matrix size of 64 cross 64 and a kernel or a filter of size 5 cross 5 with a stride 1 and no padding. What will be the size of convoluted matrix? Yeah, very simple.
60 by 60.
Correct, right?
Yeah.
So
64
64
minus
minus
5
5 plus 1.
divide by
Yeah,
1 plus 1.
correct.
59, 60 by 60.
Yeah. Option D.
So is that the formula 64 minus 5 plus 1 divided by 1?
No, no,
Yes.
64 minus 5 divided by stride, this whole plus 1.
Ah. Okay, okay. It's good you have clarified.
Yeah, this is the formula.
Right, right, right.
So this is for the padding. P is for the padding. So there is no padding, means P is 0.
Please go again, go back to the formula. Just 1 minute. I minus F plus 2P, no? Twice P
Yes.
padding. Oh, okay, by S plus 1. Okay. Okay, thank you.
Yeah. So another question. Filter size of 3 by 3 is convoluted with the matrix of 4 by 4. Yeah, simple question. There is no padding. What will be the output size?
1 cross
2
1.
cross 2.
2 cross
4
2, right?
minus 3.
2
no?
cross
Or
2,
2,
no?
2 cross 2. Yeah.
Yeah.
4 minus
2
3
by 2.
by 1
1
plus
by
1.
1.
2 cross 2.
Yes.
2 by 2.
Yeah, correct.
Yes. So then a question. Let us consider a convolution neural network having the 3 different convolution layer in its architecture. The filter size, filter numbers, the stride is given. And the question is, if the input has a dimension of 39 cross 39, what will be the overall output size?
Input dimension of the fully connected loop.
So from 39 we have to calculate for the first layer first, right? 39
Yes.
minus 3 stride. Padding is always 0. So 1 plus 36, 37 by 37. First output, right? 39 minus 3 divided by, then 37 is fed to 5. 37 minus 5 is 32.
Number of filters,
Divide.
what you
Okay,
have to do?
straight. 16 cross 16 is the output of layer 2.
Plus 1,
And
that is 17.
17.
Plus.
11,
Yes.
11 by 16 minus 5, 11 divided by 2.
7 into 7.
Yeah. So it is 7 into 7, right? So here you will get the 37 by 37. Here you will get the 37 minus
17 into 17.
17 into 70. And then here you will get 6
7
into
by
6
7.
plus 1, that is 7. So
7 by
7
7.
cross 7. Yes. And the question is then, which of the following is the input dimension to the fully connected layer? So you have 7 into 7 into 40. How much it will be? So 49 into
1960 A.
Yeah. So option A should be correct, right?
Yes.
Option A is correct. Right. The question is, suppose you have a 64 convolutional kernel of size 3 by 3 with no padding and a slide of 1 into the first layer of CNN. You pass an input to the convolution of, okay, so kernel is of 64 size 3, the stride 1. You pass the dimension through this layer. What are the dimension of the data in the next layer? So what will be the output?
Minus 3. 5 plus 1021 1022 1022 by 1022.
Yeah, so yeah, this should be 64. Okay. Yeah. So this
3.
should be, yeah.
This is not
So
correct, right? It should be
40 how we
64.
get?
Yeah, let's call it 40, 60, then it will be correct. Or call it 64 instead of 40, then option B will be correct. Right?
Can we see the
Yeah.
detailed solution? Maybe.
No, I mean, that's a mistake. They are calling
K is
as
equal
a
to 40. Okay, K is
Yeah,
equal to 40.
uh, question is, consider a CNN model which aims to classify a image as either a rose or a marigold or a lily or a orchid. So we have 4 outputs. Consider test image only has one of the image at a time. The last layer of the CNN output has a vector of logits L, which is passed through a. Okay. Yeah, so this is very simple. So we are doing the classification problem, right? And when we do the classification problem, what we do at the output layer? Softmax,
4
right?
plus.
To,
Softmax, yes, probability.
yeah, so what the question is? The layer passed through a vector of logits L that is passed through a activation that transform the logit into probability space. The
Oh,
probabilities are
transform.
more
So intermediate they are saying is, I think so.
through a law. Okay.
Pass
Yeah.
through a activation.
Hmm. So yes.
Softmax is the final one, right?
Yes,
Relu is we are using, but why leaky Relu?
Okay, so what does the leaky value mean is that, like, let's say your image is not very sharp. Okay. And okay, so in the ReLU, you left hand side, what you say, ReLU is basically max of 0 and the positive value, right?
Positive.
Max,
Yes.
I mean 0 and the value, max of 0 and the value, right? Correct?
Yes, yes.
Yes, you're right.
Yeah. So basically, when there is a negative value, it will always make it 0. And then we will say that we are not valuing the negative value. However, negative value itself is some, it has some image, okay, it has some characteristics. Okay. So leaky value tells that there is a slight negative, uh, basically, yeah, slight negative slope in the left hand side. Like let's say that has a, like let's say what it will look like. It will be look like you have a flat region and then you have a positive slope. So instead of flat, you have a slight negative slope. Understood?
Hmm.
I mean, that is called the leaky value. Like when you have a negative value, you have a smaller value instead of having a 0 value. That is what the leaky value is. Like they leak the small
So,
values instead of having making it 0.
so formula is different. Means we won't be taking the negative value as 0. Instead,
Yes,
we'll take it as a small value.
a small
But
value.
this sir has not explained till now. It is still 40 videos. I have not heard this.
Yes, yes. This is not there in the lecture. But yeah,
Uh,
like you can write a code, test for the ReLU and take test for the leaky ReLU, and then you will know that yeah, we need leaky ReLU because the features that are showing the negative kernels or the negative values because of the negative W, that is also important for us. Okay.
I understand.
Yeah.
That means
So we are
probabilities
giving,
can be there. That answer will be Likirelu.
yeah, it can't be like there is some feature there, not the probability. Probability we talk at the output, but we are
Output.
saying that, yeah. But
This
let's
is
say you are training,
intermediate.
let's say you start with some training. You, uh, you randomly picked some weights and you passed through those weights, and those weights are giving you some negative value, and then you passed it through a ReLU function. And since before you started the training and you got the value 0, then basically you lost all the information for those negative value because you have just started the random W. And so this random W is basically creating a problem for you, right? So either you will say that, okay, no, I want all the W to be positive only. Then there will be another problem, right? Understood what I mean, right?
Okay.
Yeah,
Yes.
We have to understand more. Yeah.
yeah. Suppose your input is 300 cross 300 by color, and you have a convolution layer with 100 filters such that each are 5 cross 5. How much parameter does this convolution hidden layer have? Yeah, pretty simple, right?
300
Hmm.
without bias.
300 minus 5 divided by 1, correct? Plus 1. So 296
26.
into 100, right?
See,
No.
no. Like let's say you have a filter of 5 cross 5. So that is being trained, right? And you have 100 such filter. So basically it should be 2500 as much as I understand. But okay. And let's say you have a RGB as well. So you are
Into
doing
3. Into 3.
so your answer will be 7500. Right? If you are not
Because
taking any
because
basically
RGB has 3 layers. Yeah.
yes. So basically you will have a 7500 answer, right? Simple, right? Yeah.
I think so. Let's see.
These are the
Can
following
we stay
activities.
1 second? Can we go to the detailed explanation?
Yeah, this is the same
5 into 5 into 3.
into 100.
100 such filter, which will make no bias. So 7500.
Yeah.
The bias will be there plus 1 we have to do.
Yeah, depends.
Oh,
Like
It depends
depends on
bias we are
how
having.
many layers
How
have
many bias in,
biases.
yes, okay.
like how much input you have, how much output you have, right? Like you
Yes.
have 3 input, then there will be 3 bias.
Mhm.
Yeah. Which of the following activation function can lead to the vanishing gradient?
Sigmoid
Yeah, right. Because that gradient
at
has maximum value
x
of 1 by.
very low or x very high, it will go to vanishing gradients.
Yes, because the gradients are very low at these points, right?
Yeah.
That's why I do some kind of normalization to avoid those things, right? Yeah, option B is correct. So you have a 3 statements.
Residual tools. So we have not
Okay.
learned this till now.
Yes. So
We
basically,
are till
okay.
now CNN. Yeah.
So residual network is like passing the information across the, like let's say you have a convolution layer 1, you have a convolution layer 2, and then you have a convolution layer 3. So you are passing some information from convolution layer 1 to convolution layer 3 without using the 2. So you are creating a residual between 1 and 3. So you are saying that while doing the gradient, your output is not directly related to the input as well as indirectly related to the input as well. Like input, not output. Your output is directly related to the input as well as indirectly related to the input. Indirectly related means the chain is there. And directly related means there is a residual that is directly going to the output from the input. Understood? Like you are creating a residue between, you are creating a bridge. You can imagine it as a bridge between some hidden
Skipping
layers.
skipping two or any other thing.
Yeah, skip layers basically. Yeah, right.
So what is the question here? Which is right
So,
or which is wrong?
No. Let's see. Like, so this is a correct, right? This will help to reduce the vanishing. Obviously, because there is a relation between input and output, so there will be few number of gradients in between. So there is a less chance of vanishing gradient, right? That is the correct off, right? Residual network provide residual connections straight to earlier layer.
Does it mean that CNN has a vanishing gradient problem?
Yes.
That is one of the drawbacks of CNN.
No.
Is it?
So that's why the residual layer comes into the picture, and then it eliminates the vanishing gradient problem. Okay. So the option 2 is also correct.
It's also correct, yes.
Residual network can be never be the solution of vanishing gradient problem. So this is incorrect, right?
3 is wrong.
Yes.
3 is wrong.
3 is contradicting.
So option is
1 and 2
which
are
of the
correct.
following?
C.
So, yeah. So now even without studying, you can imagine the network in your mind, right? So that is really a good sign. Yeah. The question 10 is input to the soft mesh activation function is this, and this. So what will be the output? Yeah. So obviously option A. Correct?
Actually, I couldn't understand this. How to find?
A.
So you have to find the e to the power 0.5 divided by
Okay.
e to the power 0.5 plus e to the power 0.5 plus e to the power 1.
Okay. Okay.
That is the first value.
Mhm.
Similarly, you will do the second value. Similarly, you will do the third value. The third value
Okay.
should be maximum, and the first and second should be the same.
A should be
Same.
the answer. A.
Yeah,
So A,
I mean,
option A.
even
Or
though
D
this is
is
a
also there.
no, but this is the smaller
No,
value,
because
right?
that is lesser, right? C,
Lesser.
last
Yes.
value is
Yes.
less.
Yes.
Yeah,
So
I mean,
option A.
yeah, I mean, you have to calculate it, but yeah, the
Mhm.
options are very obvious, right?
Hmm.
Yeah, yeah. So option A is the correct one. Yeah. So I hope, yeah, you can see this formula, right? So I hope this week was fruitful to you. Yeah, and you understood, and I hope you have no doubt in this week, and we will learn few more networks in this next uh, class, and then we will see what more training methods can be implemented in CNN through different networks, and we will understand the robustness and these kind of learnings we can apply to different kind of learning. It can be CNN or it cannot be CNN, but the concepts will be always be useful for different kind of training, right? So yeah.
Thank you, sir. But actually, the theory is getting more and more complicated. So practically, how much we can